Hello, my dear students. This is the third video of our lesson Basic Terms in Graph Theory. So we will discuss in this video the concepts and ideas used by Leonhard Euler in solving the famous problem and the seven bridges of Königsberg. The first term is Euler path. An Euler path of a graph is a path that contains all the edges of the graph. So we need to emphasize on the word all. So the path should passes through all the edges of the graph only once. The Euler path will begin and end with the vertex with an odd degree. So let's say this is the given graph. Okay. So among these vertices, its vertex B which has actually an odd degree. It has actually 5. Still remember that in a loop, it is in a loop considers that it has a degree of 2. Okay, so in here the degree of vertex B here is 1, 2, 3, 4, 5. Okay, another vertex wherein you can start a path is vertex C because it has three edges connected to it, or it means it has a degree of 3. So in this example, we started with vertex B. Then we have B, then A, then D, then C, going back to D, E, B, and C. So as you can see, it passes through all the given edges here only once. You can actually go back to the vertices as you can see in the name of the path AB, AD, CD, EAC. But as to the edges, it should be only once. That's for an Euler path. You may begin at one vertex and ends at another vertex. Let's say we have this given graph. In, in this given graph, we're going to determine whether there is an Euler path or none. Okay, so we need to determine first which among the vertices has an odd degree. So A has a degree of 2, C and D has a degree of 3. So you may start with C or with D. Let's try it. So we start with C. Okay, I will trace it. Then we go to B. We go to E, C, then E, E, and then we have D. It's good. So we're going to pass through that. Okay, let's try another. I think that's a first trial. It doesn't mean that you need to actually get the first one, okay? The first trial or try. Okay, let's try another one. Let's say we have here C, B, okay, we have E, and then we have C, D, E, A, B, and D. Oh, isn't it? We have able to actually trace all the lines only once. Okay, so we start with C and ends with D. Okay, so if we name that path, we actually start with C, then we proceed to E, then we go to B, then we go back to C, and then we have D, then E, then we have A, we have B, and we have E. We can number the lines. So we have 1 here, we have 2, 3, 4, 5, 6, 7, and the last one 8. So that is an Euler path. It is given graph. You can actually also start with the path CE, BCD, ED is not actually unique. You can actually find another path, okay? Another Euler path in this graph. You can try it. Okay, so let's have another one. Is it possible to determine whether a graph has an Euler path without necessarily having to find one explicitly? This question, it means that is there another method of finding or determining whether in a given graph or a given graph has an Euler path or not, aside from the one that we just did? Okay, we trace by, aside from tracing, is there another way of determining whether a graph is actually an Euler path or not? There is, actually. We use this theorem. If a graph G has an Euler path, then it must have exactly two odd vertices. So let's say we have a graph G. That's actually, to name a graph, you can use any uppercase letter like this G. And then we just determine whether among the different or the vertices, there are two vertices with an odd degree. Let's check whether this one is an Euler path or there is an Euler path in this graph. Let's count the number of vertices with an odd degree. So let's find first the degree of its vertex. So we have vertex A here. It has a degree of 2. As you can see, we have two edges connected to it. Vertex E has actually a degree of 2. D, we have 1, 2, 3, 4. Vertex C has a degree of 3. And then vertex D has a degree of 5. 1, 2, 3, 4, 5. This is a loop considered with with a degree of 2. So this one is B. So among all these degrees, 2, 2, 4, 3, 5, how many are odd? There are 2 odd vertices. We have B and C. And that actually satisfies this theorem. Therefore, in this graph, it has an Euler path. And then you can actually determine it by looking into that path. You may start with, one technique is start with the one with an odd degree. So you can start with C or B. Actually, this is our example a while ago. Okay, so that's an Euler path. We just look into the number of odd vertices. If there are exactly 2, you can actually find an Euler path in that graph. If there's 1 or 2, 1 or 3 or more odd vertices, not an Euler path. It's exactly 2. There's the word exactly 2 odd vertices. Okay? So we now proceed to another one, Euler circuit. An Euler circuit of a graph is a closed path that contains all edges of the graph. A graph that has an Euler circuit is called Eulerian. Eulerian. Okay? So in this graph, let's check whether it has an Euler circuit. Okay, so in here, it starts with one vertex and ends with the same vertex. So you can start with C here, you go to D, you go to E, then B, then this is a loop, so you go back to B, A, D, and then you go back to your starting point C, and it passes through all the edges. So it satisfies an Euler circuit. It should pass through all the edges once. Okay, so to name the circuit, we have C, D, E, B, B, A, B, C. A circuit, an Euler circuit in a graph is not unique. You can actually find another circuit in this graph. So let's try with this graph here. Okay, is there an Euler circuit? Is there an Euler circuit in this graph? So if you start with A, may I use another color here? You start with A, then you go to C, then to E, then to B, then B, then you go back to A. So it's an Euler circuit. We have the circuit A, C, B, B, D, and A. You can have also another circuit if you start with B. If you start with E, D, and C. As I said, it's not actually unique. You can actually form another Euler circuit from this graph. So same question. Is it possible to determine whether a graph has an Euler circuit without actually tracing the graph? Yes, by using this theorem. May I read it? If a graph G has an Euler circuit, then all of its vertices must be even. Okay? So all vertices must be even vertices. It means that the degree of each vertex is even. So let's determine the degree of its vertex. Vertex A. In vertex A, we have 2, a degree of 2. Vertex B, 1, 2. Then this is a loop considered 2 with a degree of 2. So we have 4 here as a degree. For E has a degree of 2. D, how about D? 1, 2, 3, 4. And how about C? 2. 2 and 4 are an even numbers. Therefore, you can say that all vertices has an even degree. Therefore, in this graph, there is an Euler circuit. Circuit.